Acid-base is a really hard topic, and that makes it great fodder for the shelf exams and for the step 2. In the first half of the video, what I want to show you is how you arrive at the primary disturbance. That is respiratory acidosis, respiratory alkalosis, metabolic acidosis, metabolic alkalosis, the differential in each one, and then if there's another test you need to do once you arrive at that diagnosis. In the back half, I want to show you how to handle an actual blood gas to determine if there's an additional acid-base derangement. This is what you'll do in life a lot, and you're almost guaranteed to get a question, what is or are the acid-base disturbances? Parentheses in the S. It's up to you to decide whether or not there are additional disturbances. So let's start off with determining what the primary disturbance is. Anytime you approach an acid-base question, you are going to start with the pH. Now I know a normal pH is 7.35 to 7.45, but if you use that, you're going to miss the multiple derangements that lead to basically normal. So what I want you to see is if at any time the pH is not 7.4, it's abnormal. And if the pH is less than 7.4, that is an acidemia. And if the pH is greater than 7.4, that is an alkalemia. Now I want you to notice that it's emia, not osis. You can have multiple metabolic and respiratory acidoses, but eventually one is going to win, and that is going to determine whether it's an acidemia, that is your blood is less than 7.4, or an alkalemia, that is your blood is less than 7 or greater than 7.4. Emia determines the primary disturbance. So you start every acid-base question with a pH, and no matter what the pH is, the next step is the CO2. I want you to see carbon dioxide as a respiratory acid, such that if the person is acidemic and it's a product of respiratory acid, it means that there is too much CO2. A normal CO2 is 40, and so if you had greater than 40 on your CO2, you have too much respiratory acid, and that leads to the primary disturbance of a respiratory acidosis, leading to your acidemia. If, on the other hand, you have an acidemia and you look at your CO2 and the CO2 is less than 40, it means you're blowing off that CO2, and therefore you have a metabolic acidosis. Because if you are blowing off your CO2, you cannot possibly have a respiratory acidosis, but you have an acidemia, which leaves behind metabolic acidosis. The same logic can be applied to alkalemia. If you believe that the alkalemia is due to the respiratory acid, it means that you have too little respiratory acid, such that if your CO2 is less than 40 and you have an alkalemia that is caused by a respiratory alkalosis. If you have an alkalemia and you expect it to be from respiratory, it should be less than 40. But if you look at your CO2 and instead it is greater than 40, it is not a primary respiratory issue, and you have metabolic alkalosis. This is not hard to arrive at, and so the questions will never end with this. But what I want you to see is you will approach every acid-base question by first looking at the pH and then the CO2 and determining what is the primary disturbance. The respiratory acidosis and alkalosis are simple. They are either hypoventilation or hyperventilation? If you do not ventilate, carbon dioxide will build up. Hypoventilation leads to a respiratory acidosis. If you're there, you only need to consider the causes of hypoventilation, the most common being opiate overdose, where the respiratory rate is simply too low. Some diseases like obstructive lung disease, either asthma or COPD with air trapping, will prevent ventilation and the CO2 will rise. A rising CO2 in either of these diseases is an ominous sign that they have a severe exacerbation. Or maybe they just don't have the muscular strength such as in someone who's been ventilated for a long time, the respiratory muscles just can't generate enough tidal volume to ventilate, or someone's just too fat and their airways are closed off, obstructive sleep apnea. But whatever the case may be, if you've arrived at respiratory acidosis, there is not a next step. You just have to find out what the cause of their hypoventilation is. The same is true of respiratory alkalosis. If you hyperventilate, you will blow off that carbon dioxide. Hyperventilation comes in pain and anxiety, the most common cause of hyperventilation, but also in instances of hypoxemia. Regardless, what you're looking for is a high respiratory rate. They are not going to trick you up with tidal volumes. That's too advanced. So in hypoventilation, look for the person who has a disease that might cause air trapping, asthma, COPD, obstructive sleep apnea. And in hyperventilation, whatever the cause underlying may be, look for the fast respiratory rate. That's it. Metabolic acidosis is by far the hardest, so let's leave it till the end. Metabolic alkalosis, if you've diagnosed that as the primary disturbance, the next test to get is going to be a urine chloride. What you want to decide is the person volume responsive? Or are they not volume responsive? Here's how the urine chloride works to determine that. If a person is volume down, that is, they would be volume responsive, the renin-aldosterone axis is kicked up. Aldosterone grabs onto sodium from the collecting duct and brings it back into the blood. It does it so that there's a concentration gradient so that when aquaporins activate via ADH, water is reabsorbed from the collecting duct into the blood. Water follows salt. Aldosterone reabsorbs sodium, but sodium can't go by itself, so it brings chloride with it. When you are volume down, the kidney tries to hold on to salt. It holds on to sodium and chloride. Thus, the chloride that remains in the urine, not that much. So if the person has a volume responsive metabolic alkalosis, the so-called contraction alkalosis, their urine chloride should be low, less than 10. If it isn't, they have another condition that is not volume responsive. Volume responsive conditions are going to be those things that lead to volume depletion. Diuretics, dehydration, and emesis. You might also see this in the way of the NG suction. The diuretics might trip you up a little bit because they cause sodium wasting, but what you should look for in the vignette is a reason why they're volume down. Emesis is a great one because it's a double hit. The pH of the stomach is low. If you vomit up acid, not only do you lose volume, you also lose acid. In particular, hydrogen and chloride. So look for clues that might give you a reason to be volume down. If you are not volume responsive, it means that you are not volume down. You have something else going on. The next step is to look for the presence of hypertension. And if you're down here you're getting to the real rare stuff that you're really not going to have to assess in an acid-base question. If there's no hypertension, you're looking at the genetic diseases like Barter's and Gilliman's. And if you have hypertension, you're looking at those hyperaldosterone states, those inappropriate hyperaldo states. Things like renal artery stenosis and primary hyperaldosteronism. You're not going to get down here on the test. So long as you identify metabolic alkalosis, get a urine chloride, you're doing good. When you see patients, just recognize that what you're assessing for is volume responsiveness. So you don't have to get a urine chloride, you can just give them volume and watch their acidosis resolve. You're going to hear words like contraction alkalosis. It makes sense if you have a contraction, your volume contracts and you get an alkalosis from being volume down. By giving them volume, you expand the volume and you get an expansion acidosis. You cannot induce acidemia this way, but you can reverse alkalosis. Let's jump over to metabolic acidosis. When you have a metabolic acidosis, your next step is to assess the anion gap. The anion gap is calculated from the serum basic metabolic profile. It is sodium minus chloride minus bicarb. If the anion gap is greater than 12, you have an anion gap acidosis. If it is less than 12, it's a non-gap. Now 12 happens to be the normal when someone has a normal albumin. For the test, just assume that 12 is normal. They're not going to make you calculate the expected anion gap based on the albumin. Just assume normal is 12. If you have greater than 12, you've got an anion gap acidosis. Less than 12, non-gap acidosis. Gap acidosis is going to be one of the mud piles. You could also use mullet sacks. Whatever the mnemonic you use, you're looking for a compound that is osmotically and acid-base active. Methanol, uremia, DKA, propylene glycol, isopropyl alcohol, lactic acidosis, ethylene glycol. Ethylene glycol is going to present with the crystals in the urine. This is antifreeze and salicylates. Just have to memorize it. Pause. Oh, we're good. We're good. Back in. And for the non-gap acidosis, what you want to assess is the urine anion gap. A urine anion gap is calculated by looking at the urine sodium plus potassium minus chloride. Now notice the anion gap in the serum and the urine anion gap rely on different electrolytes. Got to commit those to memory. Anion gap is sodium minus chloride minus bicarb. Urine anion gap is sodium plus potassium minus chloride. You're separating a positive anion gap, which means positively renal tubular acidosis, and a negative urine anion gap, which means diarrhea. Diarrhea is tricky because you think you would lose volume. And if you lost volume, you'd be in metabolic alkalosis. But in diarrhea, you also lose bicarbonate in the stool. And so the loss of bicarbonate gives you the acidosis. It's not an osmotically or an acid-active compound. It's just a loss of bicarbonate leads to an acidosis. Okay, so this is the approach and the differential for that primary disturbance. Remember, no matter what you do, start with the pH and then the CO2. Put yourself into one of these categories. If you're metabolic alkalosis, urine chloride. Metabolic acidosis, anion gap. If non-gap, urine anion gap. 1, 2, 3, 4, 5 tests can get you most of the points in an acid-base question. Let's now transition into how you determine if there's a secondary disturbance. And this is what you're going to do in real life when you start seeing patients, as well as on the